Hello students, in 12th class today I will tell you about the characteristic curves of junction diode. Characteristic curves of junction diode. Now here characteristic curves means that the curves drawn between the change in voltage to the change in current applied current through the diode. The curves drawn between the change of applied voltage across the diode and flow of current in diode are called characteristic curves. These curves do not follow Ohm's law, so they are non-ohmic. Non-ohmic curves. These curves follow exponential law. Because of it, they are called characteristic curves. Characteristic curves. When there is flow of current through the diode, there is resistance in circuit. the resistance in circuit is due to two factors. Number one, depletion layer. It stops the flow of current carriers. Namely holes and electrons. So it offers a resistance. Depletion layer offers a resistance in diode. Second, atoms during flow of current carriers the electrons holes collide with atoms and they loss their energy. It increases. It gives the resistance to the diode. So the resistance in the junction diode is because of two factors. First, the depletion layer. In depletion layer there is no free charge at all, so it behaves like a bad conductor. So it opposes the motion of the current carriers, electrons and the holes. Second, the atoms, since the electrons are moving across this depletion layer and there they collide with it and lost their kinetic energy, and this also offers the resistance to the diode. So they are main two factors which are responsible for the resistance of the diode. Thus, depletion layer in atoms in diode both are responsible for resistance of diode. And this resistance is actually of two kinds. The resistance of diode is of two types. Number one, the static resistance. When diode is connected to a DC source, the resistance is called static resistance. It is the ratio of applied direct voltage to the corresponding current in the diode. So this static resistance equal to applied direct voltage across the diode divided by the current in diode. This is the static resistance. So when diode is connected to a DC source, just like your cell or battery, in that condition, whatever resistance we are finding, that is the static resistance. And to measure it, just you find the applied voltage and then the current, the ratio of these two will be the static resistance. Second is dynamic resistance. Dynamic resistance. When AC source is applied in diode diode circuit. The resistance in diode is called dynamic resistance. Since the AC, in the AC source, the AC voltage changes with time, and you can have the alternating voltage changes with time. So now this is like this, just you can see this is suppose 0, here we are take this voltage, this is now time t, and it is like this. You can see that this is the first positive half cycle, then negative, second negative half cycle, then the positive half cycle, then the negative half cycle. So what will happen? If suppose diode in the positive half cycle is in forward wise, then for the negative half cycle it will be in the reverse wise, and then again in the forward wise, and then in the reverse wise. It means that the biasing of the diode changes with time according to this applied voltage. If junction diode is in forward biasing, for positive half cycle of AC voltage, then it will be in backward biasing for negative half cycle. Of AC voltage. It means that the resistance of the diode will change continuously. Thus, it will continue. Thus, the biasing of diode will change with time. So you can see that this positive half cycle, suppose this is in a forward, then negative half cycle, this will be in the reverse biasing. So this will change, and because of that they will changing resistance, the dynamic resistance. Because of that it is called the dynamic resistance. The resistance is no more constant, so it is called dynamic resistance. Dynamic resistance. And this is how to measure to this dynamic resistance. The dynamic resistance is the ratio of change in voltage to change corresponding change in current. It means that the dynamic resistance equal to change in voltage upon change in current. Change in current. So this is what the resistance. This is I am telling you because in the characteristic curve, so we have to find out this both kind of resistances, and this must also be clear to you that why is there resistance in the junction diode. So these two things are very necessary to know before I draw the characteristic curve in this of the junction diode. So now I will take, since the biasing is of two kinds, forward bias and the reverse bias, definitely there will be two kinds of curves. One the forward biasing curves and second the reverse biasing of the current or biasing curves. So first I am taking the forward biasing characteristic curves. Characteristic curves in forward biasing. Now we are taking to this one. Now for this you can see that this is suppose diode. This is now P, this is N. Here we have this is now milliammeter. This is source. This is now current. This is now that we have this. They are rheostat RH. Positive, negative. This is now K. The current will flow like this. This is the circuit diagram. And for measurement of the voltage across this junction diode, we have a voltmeter V. This is the voltmeter. Now here I have shown this the electrical circuit of the forward biasing and just the current. The current in circuit is given by following relation. I equal to I naught e raised to power qv upon kt minus 1. This is the required equation. In forward biasing, this e raised to power qv upon kt is very greater than 1, because here the voltage is positive, that you can see here. This is now being the forward bias. Here this part is positive and this part is negative. So P is at higher voltage than that of the N part. Therefore, I equal to I naught e to the power qv upon kt. Now here I naught is the maximum current. Where I naught maximum current, Q the charge, and V the applied voltage, and K Boltzmann constant, and T the absolute temperature. Absolute temperature. So you can see that here this follows the exponential law. It is the exponential law. Exponential law. This is what I told you earlier, that these curves will not follow the Ohm's law. They follow the exponential law, so that is given by this equation. Now as I show in the this electrical circuits, when potential difference voltage across the junction diode is increased, the current also increases. Also increases. The current carriers are majority charge carriers. Charge carriers. So now curves are like this. Here we take the current IF. This is in milliampere. on this axis. This is now suppose y-axis. This is 0. This is the x-axis, and here we have the voltage Vf. F means forward, and the curves that we get here is like this. So you see that this curve is not a straight line. Initially, when no voltage is applied, then If is equal to 0, and as the voltage is applied, then the current increases. So you can see that for Vf equal to 0, the If equal to 0. So If is forward current. Vf forward voltage. And If forward current. Forward current. Now we have to calculate the static and the dynamic resistance in this case. So you can have that if suppose we take 2 points here, this is approximately a straight line, and here we have this volt current, and if you drop a perpendicular on this axis like this, then you will find that, and this will give you the delta If so much, and this will give you delta Vf. This is suppose point A, this is the point B, this is the point C, and this will be delta Vf. So this will give you the dynamic resistance. So you can see that if suppose this is the, we take the angle theta, then you can find that the dynamic resistance this we denote by Rf. In forward wise, so this is your delta Vf upon delta If. And since If is in milliampere, so this resistance will be of order of 10 raised to the power 3. Static resistance. For this you take any point on this. Suppose you are taking this one, and just you find the voltage at this. Suppose this is now your Vf, this is your If at this point. This is the point P, suppose. So static resistance at point P. This is also denoted by Rf. Y small Rf is equal to, this is now your Vf upon If. So you can see from here that if we find the slope of this line AB, then this will be your BC upon AC. Slope of line AB, this is now your tan theta is equal to BC upon AC. So this BC is what? There is a delta IF. This is equal to delta IF upon delta VF. So this is what? Your tan theta. So if you find out this delta VF upon IF, then you can see that cot theta is equal to delta VF upon delta IF. So this is what? The cot theta is equal to RF. So if we find the cot of the slope, then you will find the resistance of this diode. So this is what in case of the forward biasing. And now if we take the reverse biasing, then the characteristic curve will be of different kinds. The resistance RF is of order of 10 raised to the power 3 ohm, because this is in milliamperes. Because of that, this is of order of 10 raised to the power 3. Characteristic curves in reverse biasing. Backward biasing. Now here we take this, the diode. This is P part, this is N part, and this is now microampere. This is rheostat, this is key K, this is positive, this is negative. So now at this time the current is very less, and just to measure this you can see that this is ammeter, this is positive and negative. Here we apply the voltmeter, and voltmeter this is positive and negative. So there will be the very less current in the circuit. It is circuit diagram of reverse or backward biasing. Backward biasing. So here just I told you about this current. Current I equal to I naught e to the power QV upon KT minus 1. So in case of reverse biasing, there is no current at all in the initial condition. So voltage is negative here. Because of that, this factor reduces to very small value. In backward biasing, e to the power QV upon KT is very less than 1. So I equal to minus I naught. It means that initially the constant current flows, which is of very small magnitude, and the current in this because of the minority carriers, because of that it is of order of microamperes. So we apply here a microammeter. Now initially when voltage across diode is increased, the current in circuit is very less due to minority carriers. And the current remains constant. If applied voltage is increased, beyond a certain voltage, the current increases abruptly. It is due to breaking of covalent bonds. Covalent bonds in junction diode. So you can see that if we have this is your VR and this is your IR. This is IR in microamperes. This is 0. This is suppose your X and this is Y. This is your Y dash and this is X dash, because current is negative. Here you see the I equal to minus I naught. So initially the current is very small. It is of this. And then it increases. X dash. So the current, the voltage at which the current increases abruptly or it increases suddenly, then that voltage is called the breakdown voltage. the voltage at which current in circuit increases suddenly is called breakdown voltage. So here you can find that this current is increasing like this. Then if we draw a straight line like this, you can see that here the current increases after this voltage. So this voltage is called the breakdown voltage, and after that it is increasing continuously. So here if we take the 2 points, suppose this is for so much, and then we take make a triangle, then you can see that this is and here we have, so this will be called delta IR, this so much, and this is called the delta VR, this so much is delta VR, and that you can find this the dynamic resistance. This is suppose the point A, and this is point B, and this we take the point C. This we make the triangle, right angle triangle. This suppose the angle theta. In triangle ABC. The dynamic resistance now this is R we denote because this is in the reverse bias, so we denote it by R, small r. RR is equal to delta VR upon delta IR. Since IR is in microamperes, so this resistance is of what very high value. It is of order of 10 raised to the power 6 ohm. And for static resistance, you can find for taking the any point here, suppose this is now point P, and this we find the voltage here, and then you find the corresponding. Now at this point, so this point, this is now suppose your IR, this is now VR, then we can take it to be, this is suppose your IR and this is your VR. Then static resistance, at point P. This is also your RR, that is equal to this VR upon IR. So now you can have that this is the point P, this corresponding to this one, we have taken IR and this is now your VR. So what we find here, that is the static resistance at the point P. Now you can see that both the resistance are of order of 10 raised to the power 6 ohm. The resistance is of order of 10 raised to the power 6 ohm. So this is about the characteristic curves, and if we draw both the curves simultaneously, then we can have like this. This is 0, this is your VF, and this is IF in milliampere, and here we have this IR in microampere, and this we have the VR like this. Then we can draw this curve, and the second one, this may be drawn as like this. This is the combined. This is for forward bias. Forward bias characteristic curve. And this is reverse bias. Reverse bias characteristic curve. And now you can also observe that there is a difference between the resistance. In case of forward bias, the resistance is of 10 to the power 3 ohm, and in case of reverse bias, resistance is 10 to the power 6 ohm. This is very high. So because of that, in the reverse bias, the diode behaves like a insulator, while in case of forward bias, the junction diode behaves like a conductor. So these are the characteristic curves and about the resistances, and then what the resistance is there, what is the meaning of resistance in case of junction diode. So now you can study this all of the video. You all like, share and subscribe. Thank you very much.